These are your instructions. In general, you just need to follow the PowerPoint. Please make sure the sound is turned up on your device so you can hear the narration. Your instructions are in yellow boxes on each slide. If a slide asks for homework, don't forget to send it in via Show My Homework, and if a slide asks for Educate to be completed, don't forget to do it by the date given.
By the end of this lesson, you should be able to describe the acceleration of a falling object, and you should be able to explain why falling objects reach a maximum velocity. There's a lot of vocabulary in this topic, and you need to be reasonably clear about what you say and what you mean by it. So let's just go through some of these keywords. First of all, in physics, a fluid is something that flows. So it can be a liquid or a gas. So it could be water or it could be air. Friction, we've met before. This is a force that acts whenever two materials move past each other. Now those two materials can be solid or liquids or gases. Drag is what we call friction caused by a fluid. So when a car moves through the air, that has drag, that experiences drag. When a submarine moves through the water, that experiences drag. Air resistance is friction caused by air. So air resistance is the force that slows your car down. And finally, terminal velocity. Objects that are falling reach a maximum velocity, and they don't get any faster than that. That velocity is called the terminal velocity. If we think back to previous work on friction, if an object has no force propelling it along, it will slow down and stop because of friction. Remember, friction always acts in the opposite direction to the movement. It is what we call a resistive force. Friction occurs between two surfaces in contact or when an object passes through a fluid. So a box being dragged across a tabletop would experience friction, and a ball bearing falling through a liquid would also experience friction. Remember, in fluids, we call that friction drag. Air resistance is a type of drag. It is caused by friction between the molecules of air and the molecules of a moving object. There are some key things that we need to know about air resistance or drag. Firstly, the size of the resistive force is dependent on the velocity of the object. As the speed or velocity increases, the size of that force trying to slow it down increases as well. That's why your car, no matter how hard you press the accelerator, doesn't continue accelerating and accelerating and accelerating. It's because at slower speeds, the force of friction is smaller, but as your speed increases, that force of friction gets larger and larger and larger. Finally, it stops you going any faster. Now, we use this idea of air resistance. For instance, when we design cars or submarines, we make sure they are streamlined to reduce drag, and that makes them as efficient as possible. The opposite side of the story is something like a parachute. Parachutes are designed to increase drag as much as possible. An important thing to understand is that if an object experiences resistance because it's moving through the air or through a liquid, if there is no air, then there's no air resistance. That means, for instance, that if you went to the moon where there is no air and dropped a hammer and a feather at the same time, they would land at the same time. In a vacuum, objects are accelerated by gravity and they fall at exactly the same speed. A very famous experiment of this is available on YouTube, and the link for you to watch it is here. Now we can draw a graph of the velocity of an object as it starts to fall. And it looks like this. When the object is first released, the force of gravity is much more than the frictional forces that is slowing the object down. So the object accelerates really quickly. But as the speed increases, the friction increases as well. Eventually, that friction reduces the acceleration until the forces are in balance. At that point, the object is still falling, but it stops accelerating. It has reached its maximum speed, or what we call its terminal velocity. So in this slide, we're going to look at the motion of a parachutist or a skydiver once they jump out of an aeroplane. It's important that you remember that there are different phases to this motion, and you need to be able to describe the motion and also explain which forces are causing that motion. So let's have a look at these one at a time. In diagram number 1, the skydiver jumps out of the aeroplane, gravity starts to act. That gravity causes the skydiver to accelerate downwards. His velocity increases very, very rapidly. In diagram number 2, we see the skydiver falling at an increasing velocity. Now we know that friction increases as velocity increases. So as he is falling, he's falling faster and faster, but the force of drag or friction is increasing as well. Now in diagram number 3, we have reached an equilibrium. Gravity is still acting upwards, but the drag has increased to the stage that the two forces match. Gravity is in equilibrium with the drag. Now at this point, we have this equilibrium, so he stops accelerating. That doesn't mean he's stopped falling, but he's now falling at a constant rate, and we call that rate his terminal velocity. Now in diagram 4, he's still falling, but when he opens the parachute, there's a sudden increase in the drag, and this causes a sudden deceleration. Basically, he's opened the parachute, and because of the shape of the parachute, the force of drag has increased very, very quickly. So for a little while, the drag is more than the gravity, and that's what causes the deceleration. In diagram 5, because of the parachute opening, the velocity with which the skydiver is falling has decreased. Okay, and because that velocity is decreased, we know that friction will decrease as well. Eventually you get to the stage where there's a new equilibrium between the force of drag, this new larger drag because of the parachute opening, and the force of gravity. And again there's a situation where there's some equilibrium, and the skydiver starts to fall at a constant velocity again because the forces on him are balanced. Now this new velocity is much lower than his original velocity, but he is still falling. Finally, in diagram 6, the skydiver is on the ground. We still have his weight acting downwards, but now we have the reaction force with the ground acting upwards. So again, he's in equilibrium. The forces on him balance, so he has stopped accelerating. If we take the motion of our skydiver from the previous slide and try and draw a velocity time graph for him, this is what it looks like. Here is when he jumps out of the plane, and all along here he's accelerating. So the rate at which he is falling is increasing. Now the acceleration starts to tail off, and by the time you get to this point here, the forces on him are in balance, and he's falling at this steady speed that we call the terminal velocity. And he carries on falling at that speed. He doesn't increase or fall any faster or slower until at this point he opens the parachute. Now when he opens the parachute, there's this sudden, really, really steep section of the curve. It's a really rapid deceleration until he reaches his new terminal velocity. Now notice that that terminal velocity is much lower than this terminal velocity, and it's that lower terminal velocity caused by the opening of the parachute that means he can land safely. And then here is where he lands on the ground. And here you can see his velocity is 0. So he's stationary here. The forces on him are again in balance and he's not moving. just to be absolutely clear, in this slide, we're comparing the motion of the skydiver before his parachute is open and after his parachute is open. Now, it's important that you remember in both cases, it's gravity which is causing the acceleration downwards, and in both cases, he reaches a terminal velocity. And that terminal velocity is when the force of resistance or drag is equivalent to the pull of gravity on him, which causes his weight. Now, that terminal velocity is different in both cases because of the shape and the area of the resistance. Follow the link to watch this video, which gives you lots of relevant detail on ideas around terminal velocity. And your final task from this lesson is to send me a picture of your work from this lesson by Friday the 19th. Thank you.